Hello class, and welcome to video lecture Sound and Resonance, taking these notes on page 109 of your interactive notebook. Let's go ahead and get started. So, we've been learning about waves, specifically things like period and frequency and amplitude and wavelength, how to graph it, what they are, what they look like, all sorts of great stuff. How does this relate to our project? You know, that thing where you have to make me an instrument. Well, all of these things are also things in sound waves. As I've already spoken about, frequency is equal to pitch, which is the note that you hear. The difference between this note and this note is the pitch, or the frequency. Now the amplitude, sorta kinda, is what relates to the volume. The bigger the amplitude, the bigger the volume. It's more complicated than that, but we don't care. And then finally, there's the wavelength. The wavelength of my note is the wavelength of my sound wave. Nothing strange or bizarre there. So, when a sound is played, those wave crests, called compressions, if you remember, enter your ear, cause all sorts of crazy stuff to vibrate. That information is sent to your brain as electrical signals, and your brain interprets that frequency as a sound. More complicated than that, of course, but you get the idea. The important thing to know is any note that has the same frequency will sound the same to us. Alright, but you have to design me an instrument. So what determines what note is being played? As we spoke about in the last video lecture, an object always plays their fundamental frequency the loudest. And this is a process called resonance. If I kick something, it is going to resonate at its fundamental frequency, at its F1, when n equals 1. It is going to make me a standing wave with one antinode. Alright, so we now know that there's some sort of relationship between speed, wavelength, and frequency. We know there's a relationship between length of my instrument and the wavelength of my wave pattern. And I know that the speed is somehow related to the material that is vibrating, be it the string or the air or the metal or the wood or whatever. If we know these three things, we can solve for them. If we know length, we can solve for wavelength. If we know wavelength, we can solve for length. If you know speed and length, wavelength, you can solve for what pitch or frequency your instrument will play. Or, in your guys' case, since pipe instruments have vibrating air, a speed of 343 meters per second, and since strings have vibrating strings, speed given by this equation, you get to choose the note that you want to play. You already know the speed of the wave, so you can calculate the wavelength. And if you know the wavelength, you can calculate the length of the instrument you need. Alright, so if it's a string wave, that's fairly self-explanatory. It's what we've been doing in lab. Things resonate, they make a standing wave of n equals 1. Hence our picture. See that you got one big antinode in the middle and a node on either end, where, if you remember, the distance from node to node is 1/2 the wavelength. Which means that the length of our string is going to be equal to 1/2 our wavelength times n, where n equals 1, so that's nice and easy. Where n is defined as any integer. It is the number of antinodes, called the harmonic number. But what about when it's air vibrating? You got something like a flute, or a clarinet, or a trumpet, not a string. Well, in that case, the end or ends that are open up to the air, those are the antinodes. They are vibrating the most because they have the most room to vibrate. If you're a closed end, it means you got air on one side and a wall on the other. You cannot vibrate as much. So, anything on a closed end is a node. So here we have an open pipe, something that is open on both ends. What we see is when vibration happens, it makes a standing wave of n equals 1, where you have an antinode on the end, an antinode on the other end, and a node in the dead center. Okay? Where n equals 1 is now the number of nodes. Oh, that's weird and creepy. Don't worry too much about it. The distance from node to node, or antinode to antinode, is still 1/2 a wavelength. So what is the relationship between wavelength and the length of my open pipe? Length equals, it's related to 1/4 of a wavelength, where n is always an even number. So, I mean, you can use the exact same equation as for a string. It will give you the right answer. But for reasons that you will see shortly, I prefer if you use this equation. If you have an open pipe like a trumpet, the notes that it will play is related to the length of the pipe. All right, now if you got a closed pipe, so this would be something like a flute. You got a wall on one side, so a node, and you got an opening on the other, so you got an antinode. In this case, the distance between node to node is still 1/2 a wavelength, so here we really do have a nice, clear, obvious 1/4 wavelength relationship. If node to node is 1/2 a wavelength, and this is 1/2 of that 1/2, that gives us a 1/4. For a closed pipe, though, n is always odd. You cannot have n equals 2 in a closed pipe. You can have n equals 3 and n equals 5, but you can never get n equals 2. Just like on an open pipe, n's always even. You can have... Sorry, something's wrong. Oh, no, sorry. No, I'm good. There. That was my mistake. Where n is always going to be an even number. So you can't have n3 or n5. You can only have 2 and 4 and 6, so on. I'll come back to this in class. Which means if you know the speed, and you know the frequency, because you chose it, you can solve for what wavelength you need. And if you know the wavelength, you can use those equations I just gave you to solve for the length. But this begs the question, why does my guitar sound different than my piano? If they're playing the same note and they're making the exact same waves, why do they sound different? Well, that's because they're not just making their fundamental frequency. They're making a whole bunch, and it's making this bizarro mix. And that mix is what we interpret as what's called the timbre of the sound, what it sounds like. Does it sound like a piano or a guitar? All right, ways that I can get this fundamental frequency to happen. Well, you can hit it or pluck it. This works for things like percussion, instruments, and strings. Or, for brass and woodwinds, you have to provide the vibration yourself, and then the instrument just magnifies it. For instance, for a string, I'm going to pluck the strings, and that is going to cause a standing wave, the volume is going to grow, I'm going to get a nice big sound. Open pipe, I'm going to blow air over the reed, which is going to vibrate a little, which is going to give me big vibrations on the other end, because of the standing wave pattern. For a brass instrument, my lips are going to vibrate a little, causing big vibrations on the other end because of the standing wave pattern. Closed pipe, this is a little more confusing. When you blow air into a recorder, it splits. Because it splits, it starts to vibrate a little bit, which causes our nice big vibrations. Same thing with the flute, you blow over it like this, but some of it splits and goes that way. Same with the bottle, you blow across it like that, but some of the air goes inside. So in all these cases, you get a little vibration at the opening, and big vibration on the other end. Percussion, you hit it, and it makes a much larger vibration. Crazy. A question for you, do you suppose that these drums right here count as open pipes or closed pipes? The and bring all your questions to class.